Hello students, welcome to the class. So we are going to begin with a new topic, that is equilibrium. Okay. See, equilibrium, something related with the reactions. Whenever the word equilibrium comes into context, yes, whenever we speak about something, not only in chemistry, I'm saying whenever we speak about something in equilibrium, immediately we get a picture in our mind of an object under influence of two opposing forces. Yes or no? So equilibrium can only be achieved when there are two opposing forces, one in different directions. Yes, both should be in opposite directions. For a chemical reactions also, this is true. A reaction also can exist in the state of equilibrium, balancing the forward and backward reactions. Okay, so first let us try to understand certain concepts, then we will move to what is a forward reaction, what is a backward reaction, and then we will try to put this concept of equilibrium into our chemical reactions, right? So before going to that, we need to first understand what is reversible and irreversible reactions. See, when we were discussing thermodynamics, there itself we have discussed regarding reversible and irreversible reactions. Okay, see, a chemical reaction is said to have taken place when the concentration of reactants. So we know that chemical reaction means what? When we speak about a chemical reaction, yes, I mean here we have reactants, yes, which are forming products. Yes, let me write it like this, products. So if you see, before starting the reaction, the concentration of this is what? This is my reactants. Yes, this is my reactants. And these are products. So in the beginning, when I talk, the concentration of the reactants will be more. So concentration will be more here. And in the beginning itself, initial concentration, if I speak, the initial concentration means what? Before starting the reaction. I'll be having only reactants. Do I have products? No. Product concentration will be what? Product concentration will be 0. Yes. So as the reaction proceeds, the concentration of reactants goes on decreasing and the concentration of product goes on increasing. This is what happens, right? So it goes on increasing here. So a chemical reaction means what? A chemical reaction is said to have taken place when the concentration of the reactants, and the concentration of the products in concentration of the reactants decreases and the concentration of products increases. Product increases, correct? So this is called what? We say a reaction, a chemical reaction has occurred. So concentration of the reactants goes on decreasing and the concentration of the product goes on increasing with what? With time, as the time progresses. Correct. So the chemical reactions, based on this, the chemical reactions are classified on the basis of extent to which they proceed. They are being classified into two types. Yes, they have been classified into two types. And those two types are, the first one is reversible reaction. Reversible reaction. We have discussed about reversible reactions in our thermodynamics, but here we are going to see it under a different scenario. Okay, fine. So what do we mean by reversible reactions? Reactions in which entire amount of reactants is not converted into product is called as reversible. Yes, see, different way I'm defining. So what do we mean by reversible reactions? Reaction in which entire amount of reactants is not converted into products. Why I'm saying so? Because in a reversible reactions, what happens? As the reaction is proceeding forward, then the reaction also, see, ice getting converted. I'm not taking about this ice getting converted into water is not a chemical reaction. Okay, it is a physical change. Ice getting converted to water. Let me say I've taken 10 grams of ice cubes. 10 grams of ice. It gets converted into water. If I apply here if I reduce the temperature of water, again that water will get converted back to ice. So entire amount of reactants is not converted into products. That we call it as reversible reaction. Then we also have seen the characteristics. What are the characteristics of reversible reactions? Yes, what are required in this topic, we'll discuss those important characteristics. The first characteristic says that these reactions can be started from either side. You can start it from reactant to product, or you can start it from product to reactant. Either side you can start it, because entire amount of reactant does not get consumed. Therefore, you can start it from reactant to product or product to reactant. Right. Then, second important characteristic is that these reactions are never complete. So reversible reactions are never complete. See, when a reaction gets completed, tell me, when all the reactant gets converted to product. But reversible reactions are those in which entire amount of reactant is not converted into product at any time. At any time, it will not get what, because as the reactants are reacting to form product, similarly, in reversible, products will react back to form the reactants. So at any instant of time, there will be some amount of reactant as well as some amount of product. Therefore, we can say the reaction is never complete. Okay. Next point is that these reactions have a tendency to attain state of equilibrium. Yes, they attain the state of reaction where the concentration of the reactants and concentration of the product does not change with the time. I'm not saying it will remain 50-50. See, entire equilibrium topic, when you understand, you will get to know what does this mean. Yes, when we say concentration of reactant and product does not change with time, it is not that here we have 50% of reactant and 50% of product. No, it is not like that. Okay. So here, these reactions, they have the tendency to attain equilibrium. So these reactions attain equilibrium means what? With what speed the reaction is proceeding in forward direction, with the same speed the reaction will proceed in backward direction at certain point during the progress of the reaction. That time we say it has attained the equilibrium. And we know that for any reaction at equilibrium, what is the free energy change? Gibbs free energy change. So Gibbs free energy change at equilibrium is equal to what? It is equal to 0. Therefore, the reversible reactions, they have the tendency to attain the state of equilibrium where the Gibbs free energy change is 0. It is 0. Next is, we represent this reversibility reaction by certain symbol. The symbol used is either you can show it like this. Yes, this represents forward reaction and this represents backward reaction, or sometimes it is shown like this also. But the better way to represent the reversible reaction is this one. Yes, okay. Excuse me. This represents the reversibility of the reaction. Okay. So these are some of the characteristics of the reversible reactions. Let us consider some of the examples to understand the reversible reactions. So examples for understanding the reversible reactions. The first example is neutralization reaction between acid and base, either of which or both are weak acids. So you can either take one strong acid or one weak acid, or you can take a strong base or a weak base, or both can be strong and weak. Let me consider. So I'll write the reaction here, what I'm talking about. It is a neutralization of acid and base. Okay, and you know that neutralization of acid and base leads to what? It leads to formation of salt. Let me take this reaction. CH3COOH. This is called acetic acid. Yes, it is a weak acid. Okay, when it is treated with a strong base, say NaOH, sodium hydroxide, it undergoes neutralization. Acid and base undergo neutralization to give salt. The salt obtained is CH3COONA plus water is formed, right? So here, when I'm writing this reaction, I will not use this symbol. I will use the symbol this. So what does that mean? It means it is an example for reversible reaction. As soon as this water formed is not removed, again water will react with the salt and form back my acid and base. Is that right? So neutralization, C reaction. Second, reactions like salt hydrolysis are also examples for as reversible reactions. For example, you take any salt, FeCl3, say for example, and make it undergo hydrolysis using water. Yes. So what do we get? It is a reversible reaction. So I will indicate it by this symbol. Then I get FeOH3 thrice ferric hydroxide plus I get HCl. Yes, this is obtained. Ferric hydroxide plus HCl. Is that right? So this is the reaction. Moving to this next example, that is thermal decomposition. Yes, thermal decomposition means what? Thermal decomposition means breaking something, breaking a compound in presence of by applying heat. Thermal decomposition, right? So breaking a compound by apply of heat. Let me say I have phosphorus pentachloride. It will undergo thermal decomposition in presence of heat to give phosphorus trichloride plus Cl2. As soon as the Cl gas is not removed, then what happens? Then these two will combine and form back PCl5. Therefore, either I show heat here or I will say minus delta H. That means energy is absorbed. Minus means what? Yes, energy is absorbed. Or you can remove this and say you don't write it with the reaction, and then you can say delta H is what? Delta H is positive. I can say for a reaction, delta H is positive. That means energy is absorbed. Energy is absorbed. Correct? Okay. For one more very important example is, it is esterification reaction. See, these are chemical reactions which we'll be discussing when we are studying organic chemistry topics of second PUC. Okay, so esterification reaction means what? When an acid and alcohol are treated. Yes, I will take this acid CH3COOH. It is treated with alcohol C2H5OH. Yes, C2H5OH in presence. I'll write this reaction once again. Okay, so here CH3COOH plus C2H5OH. So what type of reaction it is? It is reversible reaction, which gives me what? In presence of an acid. So in presence of H plus. That is, I take H2SO4 here. What do I get is, I get CH3COO C2H5 plus H2O. Okay, so this compound, the compound formed, it is called what? It is called ester. It is called ester. Therefore, this reaction is called esterification reaction. See, this is the basis of manufacture of our soap, students. Soap is manufactured using this reaction itself. Yes, esterification reaction. But here we do not take H plus ion. Instead, we consider sodium hydroxide. So this is all about reversible reaction. Even you can quote an example. For this, you can quote an example of evaporation of water in a closed vessel. Yes, evaporation of water in closed vessel. See, when you carry out evaporation of water in closed vessel, what happens? H2O, it undergoes evaporation. H2O, it gets converted to gas, and how it will get converted to gas? You are applying heat here. Therefore, I can say delta H is positive here. Delta H is positive. Correct. So these are all examples for what? Reversible reactions. And this is the symbol used to represent the reversible reaction. Okay. Moving to second type of reaction, that is what? It is irreversible reaction. Irreversible reaction. So what do we mean by irreversible reaction? The reaction in which entire amount of reactants are converted into products. Yes. So reaction in which entire amount of reactants are converted into products. That means there is no other way that products may get converted to reactants. Entire amount of reactants are converted to products. So when I show a reversible reaction, I write it like this: A plus B gives me product. Yes, entire amount of reactant gets converted to product. Is that right? So what are the characteristics of irreversible reactions? What are the characteristics? So we saw the characteristics of reversible reactions. Now, what are the characteristics of irreversible reactions? These reactions proceed only in one direction. They are one direction reactions. They proceed in only one direction, and that direction is called what? It is called forward reaction. Forward reaction. See, the reactants getting converted to product is forward reaction. The reactants, the product getting converted back to reactants is backward reaction. Yes, we have seen here. So here we have seen. Correct? So here we have seen this. Reactants getting converted to product is what? It is forward reaction. Correct? And the products getting back converted to reactants is what? Backward reaction. Backward reaction. Correct? So in case of reversible reactions, we have forward as well as backward reactions. Whereas when we talk about irreversible reactions, we have only, it proceeds only in one direction. That is also forward direction. These reactions, they proceed for completion. They proceed for completion. Yes, they proceed for completion. Yes or no? Because there is no concept of backward reaction. Therefore, they proceed for completion with the time. For an irreversible reaction, delta G is not equal to 0. Instead, delta G is less than 0. For any irreversible reaction, delta G is what? It is less than 0. Correct? That means there is no point of attaining the state of equilibrium. And for representing irreversible reaction, we use this arrow mark. We use normal arrow mark for representing the irreversible reaction. It is placed between reactants and products. Correct. So let us take examples of irreversible reactions. Yes, so many examples we have. Yeah. So what are the examples? The first one is neutralization between strong acid, strong base. See, there also we have seen the example, neutralization of acid and base, out of which one at least should be strong and one should be weak. Here, if you take a strong acid and strong base, then we call it as irreversible reaction. We call it as irreversible. For example, HCl plus NaOH, both are strong acid and strong base. I will get NaCl plus H2O. Acid base gives me salt and water. Yes. Then second example is, so if one of the acid or base is weak, then it becomes reversible reaction. Second one, double decomposition. Yes, double decomposition reactions. Double decomposition reactions, or these are also called as precipitation reactions. What they are also called as precipitation reactions. I'll just tell you why they are called so. Yes, and why are they irreversible reactions. Let us take an example of barium chloride plus H2SO4. It will form what? It will form barium sulfate plus HCl. See, barium sulfate formed, it is nothing but precipitate. It is what? It is precipitate. It will remain at the bottom. So once precipitation is formed, I cannot expect both of them to react and give back the reactants. Yes. So precipitation reactions are what? Precipitation reactions are irreversible reactions. Even some of the thermal decomposition reactions also. Thermal decomposition of potassium chlorate you can take. Yes, thermal decomposition. The example comes here when KClO3 is thermally decomposed in presence of MnO2. Yes, what we get is we get KCl plus O2. A gas it is, it will escape out, leaving behind only KCl. Even the redox reactions, some of the redox reactions are irreversible. Redox reactions, yes. Redox reactions, we have seen what do we mean by redox reactions. Oxidation and reduction take place simultaneously. SnCl2 plus FeCl3 gives me what? It gives me SnCl4 plus FeCl2. Yes, so you can see here, how can I call it redox? Here, this is -1 into 2 -2. So Sn is +2, correct? And here Fe -3. So Fe is +3 here. And here Sn, this is +4. And Cl is what? Fe is what? Fe, it is +2. So you can see here, there is change in the oxidation state of stannum, that is tin, from +2 to +4, and Fe, there is change from +3 to +2. So increase in oxidation number is what? It is oxidation, loss of electrons. Decrease in oxidation number is what? It is reduction, that is gain of electrons. So here both are taking place. Therefore, I call it as what? I call it as a redox reaction. So these are all examples for irreversible reactions. Yes. So with this concept in mind, so we will try to give explanation for equilibrium and its dynamic nature. So equilibrium is always dynamic in nature. It is not static. So equilibrium and its dynamic nature. Okay. So now see, equilibrium means what? Equilibrium is the state at which, yes, I'll write it here because first time we are discussing this concept. So equilibrium is a state at which equilibrium is a state at which the concentration of reactants and products do not change with the time. Yes, that is concentrations of reactants and products remains constant, or you can say becomes a constant. This is the definition of equilibrium. So equilibrium is a state at which concentration of the reactants and products do not change with the time. Now, what do we understand by all these things? See, students, when we speak about equilibrium, when I talk about a chemical reaction, reactants getting converted to products. Okay. So initially, when I say initially, that means before the start of reaction. At initial state, the concentration of the reactants will be maximum and concentration of the product will be zero. Yes. With the progress of time, try to understand this concept very properly. With progress of time, what happens? So a concentration of reactant goes on getting converted into product. So with the progress of time, concentration of reactant decreases and slowly concentration of product increases. Now see, when this is happening, when reaction has started, what is this reaction? This is forward reaction. Okay, this is forward reaction. So when reaction has started in the beginning, since concentration of the reactant is maximum, yes, therefore the forward reaction will proceed very fast. Yes, and that speed of a forward reaction or speed of any reaction, it is measured as rate of the reaction. So rate of the reaction means what? With what speed the reaction is progressing. So whenever we talk about rate, it is nothing but velocity of the reaction with respect to time. Whenever we use the term rate, it is with respect to time. Okay. So velocity with the time. I call it as velocity. I do not call it as speed because speed is in only one direction. Velocity is in both directions. Therefore, I use the term velocity. Velocity of the reaction with the time is nothing but rate of the reaction. So since the initially state reactant concentration is maximum, therefore rate of forward reaction is high. Correct? It is high, and I represent rate of forward reaction as RF. Okay, understood. So product concentration is zero. Therefore, in the beginning, there will be no product concentration. Correct? There won't be any product. What you say? There won't be any product. Therefore, there won't be any backward reaction. But as the reaction progresses with the time, concentration amount of reactant goes on getting converted into product. So as concentration of reactant decreases, concentration of the product increases. So with the concentration of product, I expect the rate backward reaction also taking place. So what is this? This is backward reaction. So with the time, the rate of backward reaction slowly increases. Yes. So at the end of the reaction, if suppose we speak at the end, what happens? The rate of backward reaction backward reaction will be high. And when it will be high? At end of reaction. This is at the initial state, initially. Correct. So when all the reactant is almost getting converted into product, or you can say as the concentration of a product increases, correct, the rate of backward reaction, it becomes high. So forward reaction is also occurring, backward reaction is also occurring. In the beginning, forward reaction is occurring very fast because the concentration of reactants is more, and backward reaction is almost zero because there is no concentration of the product. But with progress of time, when amount of reactant starts getting converted into product, what happens? The rate of for backward reaction also begins. So in the beginning, it is almost zero, or it will be less. As time progresses, when maximum amount of reactant has got converted into product, that time what happens? The rate of backward reaction will be high. So since the rate of backward reaction will be high there, and forward reaction will be what? It will be so less, because at the final time, what happens? This will almost come, it is not zero, okay? If the concentration of the reactant will be less, concentration of the product will be more. So in the beginning, rate of forward reaction is high. At the end, rate of backward reaction is high, but the reaction doesn't stop. So as backward reaction is happening means what? That time concentration of reactant goes on increasing again, and concentration of product goes on decreasing. So this happens, this continues in the forward reaction. That's the reason in reversible reactions, what we say, these reactions are never complete. Yes. So when this is happening, in the beginning, rate of forward reaction is high. At the end, rate of backward reaction is high. In the beginning, concentration of reactants is more. At the end, concentration of products is more. But during this progress of the reaction, a state is reached, a point is reached where the forward reaction and the backward reaction both will occur at the same rates. Yes. So what I mean to say is, at certain point during the progress of the reaction, the rate of forward reaction will be equal to rate of backward reaction. Understanding? Rate of backward reaction. And that point is called what? That point is called as equilibrium. The rate of forward reaction and the rate of backward reaction becomes same. Yes, with what velocity the forward reaction is progressing, with the same velocity the backward reaction is progressing, because the concentration, because concentration of reactants and concentration of products remains constant. It is not equal, students. It remains constant. So that is what that is called as equilibrium. So equilibrium is a state at which the concentration of the reactants and products do not change with the time. That is, the concentration of reactants and products becomes constant. It becomes constant. So if you want to show the same in the form of graph, you can show it like this. Yes, we can indicate it like this. If I indicate this as the progress of the reaction, if I indicate here as the progress of the reaction, and if I indicate in x-axis the progress of the reaction, and y-axis if I indicate the concentration, at y-axis I will indicate the concentration, then okay, here I'll indicate it like this. Y-axis I will indicate the concentration. Okay. Yes. So I'll indicate it. Fine. Okay. Okay, fine. So if I indicate this with as the concentration, so what happens? So I will write here, this is nothing what? This is time. Yes, this is time. Or you can call it as progress of reaction, because progress of reaction happens with the time. So progress of reaction. And here I will indicate it as concentration. Yes, I'll not say reactants or products. Now we can say that in the beginning, yes, suppose I have reactants which is forming me product. So in the beginning, whose concentration will be maximum? In the beginning, the reactant concentration will be maximum. So I'll say concentration of reactants is somewhere here. So this is what. Always remember, students, when we want to write about the concentration, how we represent concentration is, we will write, suppose, concentration of reactant. So I will write it into box bracket. I'll say, I will write it like this. So how do you pronounce this all? You say concentration of reactants. Box represents concentration. And if you want concentration of products, how do you write it? Concentration of products. This we represent it like this. So whenever any reactant or product I'm writing into box bracket means what? I'm saying about concentration. I'm speaking about concentration. Is that clear? Okay. So here comes what? Here comes. So at the beginning, concentration of reactant is maximum. So let me say this is concentration of reactant. And at the beginning only, the concentration of the product is 0, right? So I will say this is what? This is concentration of the product. So concentration of the product. So as time progresses, with the time or as the progress of the reaction happens, what happens to the concentration of the reactant? The concentration of the reactant goes on. Yes, the concentration of the reactant goes on decreasing. The concentration of the reactant goes on decreasing, correct? It goes on decreasing like this. And as the time progresses, the concentration of the reactants goes on decreasing. So I can write it here. This is what? This is reactant concentration decreasing. See, I have not touched the line to y-axis. It has not become 0. Correct. Okay. And then as the time progresses, the concentration of the products, what happens to the concentration of the product? It goes on increasing. It goes on increasing. Correct. So concentration of the products goes on increasing. So this is the concentration of products, right? So are you all understanding the graph? So this is concentration of the reactants, which is going on decreasing. This is concentration of the product, which is going on increasing. Yes. So here what happens? Can you see here? Now, can you make this distinction here? You can see here, this is the term where, can you see this point here? If you see here, if you go on enlarging it, we can see that this point, yes, this point, okay, I'll indicate it with different color. So this is the point where the concentration of a reactant and the concentration of a product remains constant. So can you see this point? So at this point, the concentration of the reactants and the concentration of the product remains constant. So this point is called what? This is called equilibrium state. We call it as equilibrium state. So what do we mean by equilibrium? The concentration of reactants and concentration of products remains constant. It is not same, students. It remains constant. Okay, that state is called equilibrium state. Or I can represent it in a different form also. To understand the different form, let us try to understand the characteristics of equilibrium, or the characteristics which are involved in the state or to attain equilibrium state. So what are the characteristics? Okay, so see here, characteristics of equilibrium state. The first point is equilibrium state can be recognized by the constancy of certain measurable properties also. Looking at the constancy of certain measurable properties, you can recognize equilibrium. And those properties are nothing but you can recognize it by pressure. You can recognize it by density. Change in density, you can recognize it by change in color. You can recognize it, most important, change in concentration of reactants and products, right, etc. By changing these conditions on the system, we can control the extent to which the reaction proceeds. Okay, this is the first characteristic. The second is equilibrium state can only be achieved in closed vessel, students. It can only be achieved in closed vessel. If the vessel is closed, then only you can. Closed system where there is exchange of only heat, there is no exchange of matter. See, if see why I say closed vessel is because, students, suppose let me say if I have taken a vessel And into this, if I've taken an open vessel, now see, when the reaction happens, I cannot always expect to the formation of only solid products, right? Sometimes gaseous products are also formed. For example, if I'm carrying out this reaction of PCl5 PCl5 decomposition, it will decompose to give PCl3 plus a Cl2. This chlorine gas, if the vessel is open, if the system is open, chlorine gas escapes out. When chlorine gas escapes out, some amount of chlorine gas, at least if it escapes out, I cannot expect the backward reaction to occur properly. Therefore, what is the condition? The vessel should be closed. You should carry out decomposition reaction. Sorry, you should carry out reaction in a closed vessel to expect equilibrium, for a reaction to attain equilibrium. So equilibrium state can only be attained in closed vessel, and equilibrium state is reversible in nature. Equilibrium state is reversible in nature. Only for reversible reactions we can explain equilibrium state. Equilibrium state is dynamic. It is not static, students. Yes, suppose in the beginning I said concentration of the reactants is more, so rate of forward reaction will be more. At the end, concentration of products is more, therefore from there rate of backward reaction increases. So when equilibrium is attained, with what speed the rates of both the backward as well as forward reactions remains same. That means the reaction will be still progressing. It will not stop. It will not come to end at equilibrium. They will progress with the same rates. The rate of forward reaction will be equal to the state of backward reaction. Therefore, we say equilibrium state. Equilibrium is dynamic in nature. It is static. So at equilibrium state, what can we say? Very, very, very important point. That is rate of forward reaction is equal to rate of backward reaction. Rate of forward reaction is equal to rate of backward reaction. Very, very, very important point. The rate of forward reaction is equal to the rate of backward reaction. That means with what speed the forward reaction is progressing, with the same speed the backward reaction will progress, and that is said to be the reaction is said to have attained the state of equilibrium. It has said to have attained the state of equilibrium. Is that clear? So don't get confused. The rate of forward reaction will be equal to the rate of backward reaction. Yes, or I can write it like this also. Rate of forward reaction is equal to rate of backward reaction at equilibrium state. So how can we explain this? This is very well explained. Again, I can explain you graphically only. So if I say this is, let me say this is progress of the reaction. Okay, so this is my progress of the reaction. Okay, done. Then here I will take concentrate, or let us consider here rates of the reactions. Okay, so I will mention here, this is what, this is my, in this direction. Okay, so this is the rate of reaction. Rate of reaction means what? The reaction occurs with what velocity, what speed you can say. And this is what? This is time, or you can call it as progress of reaction also. So in the beginning, since concentration of reactants is more, here will be the concentration of reactant, correct? So then since the concentration of reactant is more, I'll show it here, and here concentration of product I will show. So I will write it like this here. This is concentration of reactant, and this is concentration of product. So since concentration of the reactant is more in the beginning, rate of forward reaction will be more. So here the rate of forward reaction, it will be more. So this is RF, rate of forward reaction. And rate of backward reaction, in the beginning it will be zero only, because reaction has not started only. As a reaction progresses with the time, what happens to the rate of forward reaction? The rate of forward reaction goes on decreasing. Sorry, let me indicate it properly. the rate of forward reaction goes on decreasing, correct? It goes on decreasing. Yes, we can say it goes on decreasing like this. Okay, fine. So it goes on decreasing. Understood? Okay, I want to indicate it properly. Yes, it goes on decreasing like this. So here I can mention it like the rate of forward reaction. So forward reaction goes on decreasing with the time. Then what happens to the backward reaction? As the reaction starts, the rate of backward reaction goes on increasing. The rate of backward reaction goes on increasing. So this is what? This is backward reaction, correct? It is 0 in the beginning. It goes on increasing. Yes. Then a state is reached where the rate of forward reaction and the rate of backward reaction will start proceeding. They become same. They become same. So you can see here, from here, I can say it proceeds like this. Is that right? It proceeds like this. So what does this mean? It means at certain time, what happens? The rate of forward reaction, which is going on increasing, decreasing with time, and backward reaction, which is going on increasing with time. So this is rate of backward reaction. This is rate of forward reaction. It is decreasing with time. This is increasing with time. At certain point, both the reactions will occur with same speed. See, the speed is same. Backward reaction speed is also same. Forward reaction speed is also same. Yes, and that point is called what? That point we call it as equilibrium. Yes, that point is called what? It is called equilibrium state. It is called as equilibrium state. Yes, so I call this point as equilibrium state. Yes, so what is equilibrium state here? The time at which the system reaches equilibrium. So this is the time at which the system has reached equilibrium, where the rate of forward reaction is equal to the rate of backward reaction. And see, both the reactions are occurring with the same speed, So it is occurring only. It is going on with the same speed. It has not stopped here. Did I say it stops here? No, it is occurring with the same speed from this particular point. Therefore, we say equilibrium is dynamic in nature. Equilibrium is dynamic in nature. So with this all understanding, there are basically types of equilibrium. There are 4 types of equilibrium. Yes, the types of equilibrium. Equilibrium in a system, it implies to what? It implies the existence of following 3 types of equilibria simultaneously. The first one is thermal equilibrium. Thermal equilibrium. So when we speak about something related to thermal, it means we are talking about something about temperature. So the thermal equilibrium means what? At that state, there is no flow of heat from one part to another. That is, I can say T remains constant. So how their reactant concentration and product concentration is remaining constant. Similarly, in thermal equilibrium, when the equilibrium state is being attained, T remains what? T remains constant. Temperature remains constant. The second one is mechanical equilibrium. Mechanical equilibrium. So mechanical equilibrium, there will be no flow of matter. Here thermal equilibrium means what? No flow of heat from one part to another. Mechanical equilibrium means what? No flow of matter from one part to another. There will be no flow of matter from one part to another. That is called mechanical equilibrium. Yes, where we say P remains constant. P remains constant. Yes, it remains constant. The third one is physical equilibrium. Physical equilibrium. So physical equilibrium means there is the substance exists in 3 states. Our solid, liquid, and gas. So substance exists in the 3 states. And last one is chemical equilibrium. Chemical equilibrium. That is, there is no change in the concentration of any part of the system with the time. No change in the concentration. In this topic, we are going to discuss on two concepts, two equilibria: physical equilibria and chemical equilibria. Yes, so physical and chemical equilibria we are going to discuss. So what all we discussed now? Equilibrium and its dynamic nature. You understood why it is said to be dynamic? Yeah. So equilibrium is what? It is a state at which the concentration of the reactants and products do not change with time. That is, the concentration of reactant and products becomes constant. Yes. So if reactants are getting converted to product, we call it as forward reaction. Products getting back converted to reactants, backward reaction. So in the beginning, since reactant concentration is maximum, rate of forward reaction is very high. And since product concentration is zero, backward reaction is zero. As time progresses, the concentration of reactant goes on decreasing and concentration of product goes on increasing. Therefore, the rate of forward reaction goes on decreasing and the rate of backward reaction goes on increasing. So in the beginning, forward reaction is occurring at a high speed. At the end, backward reaction is occurring at a high speed. But the state is reached, a point is reached where both the reactions will occur at the same speed. Because at that particular point, the concentration of reactants and products will be constant, not the same. It will be constant. And that is called what? It is called equilibrium. Correct? And we have seen this. This is the graph for concentration. So concentration, you represent it like this. Concentration of reactants goes on decreasing with time. Concentration of products goes on increasing with time. And this point where, from where, see, concentration of product and concentration of reactants remains constant. It remains constant, and that is called, see how much it was, it will remain that much only. How much product concentration was, it will remain that much only. That state is called equilibrium state. And we have seen the types of equilibrium state. Characteristics. So should be carried out in a closed vessel. It is reversible, dynamic. At equilibrium state, the rate of forward reaction will be equal to the rate of backward reaction. And that is called as the state of equilibrium. Yes, and we have seen the types. So reversible and irreversible. Now moving to what I said, we are going to discuss two concepts, that is physical equilibrium and chemical equilibrium. So chemical equilibrium means what? We have seen that just now I spoke about it. State of a system in which concentrations of the reactants and the concentration of the products does not change with time. And the system does not display any further change in the properties. Any further change in the properties, right? Okay, so this is what chemical equilibrium. So here we'll be speaking about concentration. Fine. Physical equilibrium, we'll be speaking about the three states, that is solid, liquid, and gaseous state. Now, why the chemical equilibrium? Or not only chemical, here we are talking about reactants and products, so we take chemical. In general, chemical equilibrium is said to be dynamic. The state at which we have seen just now the graphical representation of a forward reaction and backward reaction, right? The stage at which the rate of forward reaction is equal to the rate of backward reaction is called what? Equilibrium stage, or you can call this as equilibrium state. At this point, the number of reactant molecules converting into product and the product molecules converting into reactants are same. See students, concentration of reactant and product is not same. How many molecules are getting converted into reactant and how many molecules are getting of product are getting converted into, sorry, how many molecules of reactants are getting converted into product and how many molecules of product are getting converted into reactant, it will be same. I'll give you simple example. Suppose you all are standing outside in your college. You are standing in a ground. As soon as your prayer gets over, you have to enter to your respective classroom. Let me speak about a one division class. So what the students will do, in the beginning, the number of students in the ground is more, whereas in the classroom it is zero because all have come for prayer. Yes. So what happens? The concentration of the students in the ground is more. and concentration of the students, that is number of students in the classroom, is 0. So what will happen? All the students are getting into the classroom. So movement of students from ground to classroom, so that is the rate, the speed, that is more. Yes. Now what they say, as soon as you go into the classroom, you have to come out to get something, okay, and enter back to your classroom. Therefore, some students, as soon as they go inside, they will try to come out. So here students are entering, and some students who have entered, they are coming out now. So in the beginning, the students entering the classroom, that speed was more, and students entering out from the classroom was 0. So as time progresses, as the number of students in the classroom increase, the speed at which the students are coming out from the classroom also increases. During this happening, where students moving from ground to classroom and classroom to ground is going on, a state will be reached where the number of students entering from ground to classroom and the number of students entering from classroom to ground is the same. Understanding? I'm not saying that how many students are there in the ground, the same number of students are there in the classroom. No. The number of students entering from ground to classroom and from classroom to ground remains same. That here, if you want to say, number of reactant molecules getting converted into product and product molecules getting converted into reactants are same, and that state is called what? That state is called equilibrium. Therefore we say reactants and product concentration remains constant, not same, remains constant. Yes, so that is said to be equilibrium. And because of this, what happens? The rate of forward reaction at certain stage, the rate of forward reaction and backward reaction becomes same. So the same equilibrium can be carried out with the same reactants anywhere with similar conditions with continuous interchanging of the molecules. Hence, dynamic equilibrium. Hence, chemical equilibrium is what? It is dynamic in nature. You can see a simple example I've taken. I'll explain this reaction once again later when we move into the deeper into the concept. So here you see the N2 plus 3H2 is giving NH3, and it is a reversible reaction. You can look at the arrow marks. Looking at the arrow mark, we can say at equilibrium what happens? Now, what I call here forward reaction, tell me. Here, forward reaction is N2 and H2 getting converted to NH3. NH3. This is what? This is forward reaction, correct? So in the beginning, since nitrogen and hydrogen concentration is more amount of N2 gets N2 and H2 react to get converted to NH3. So forward reaction will be occurring with high speed. After certain interval of time, with the progress of reaction, when the concentration of product increases, it will get back converted to N2 and H2. So this is what? This is backward reaction. Backward reaction. And rate of backward reaction, after certain time, it goes on increasing. At equilibrium stage, yes. So at equilibrium state, what happens? The rate of forward reaction will be equal to the rate of backward reaction, or concentration of reactants and concentration of products remains constant. It remains constant. So this is called equilibrium. So at equilibrium, the rate of forward reaction is equal to the rate of backward reaction. And we have something called equilibrium mixture. So the mixture of the reactants and products in the equilibrium state, mixture of both reactants and products in the equilibrium state is called equilibrium mixture. What it is called? Equilibrium mixture. So when the rate of forward reaction is equal to the rate of backward, or you can call it as reverse reaction, the state of chemical equilibrium is achieved by the system. When there is no further change in the concentrations of reactants and products. Why there is no change in the concentration of reactants and products? Due to equal rates of forward and backward reaction, the system is said to be in the state of dynamic equilibrium. So you can see here, this is concentration versus time graph. In the beginning, the rate of concentration of the reactants is more, sorry, the concentration of the reactants is more. In the beginning, the concentration of the products is 0. As with the progress of time, rate of concentration of the reactants goes on decreasing, and concentration of the reactants goes on decreasing and concentration of the product goes on increasing. From this point, you can see the concentration of both reactants and products remains constant. It remains constant. That is called equilibrium state. Or when you show a rate of reaction with the time, we say in the beginning rate of forward reaction is fast. As with the time it goes on decreasing. In the beginning rate of backward reaction is 0. With the time it goes on increasing. A state is reached where both the reactions will start occurring at the same rate. So rate of forward reaction is equal to rate of backward reaction, and this state is called what? This state is called equilibrium state. It is called as equilibrium state. Is that right? So a graph with concentration on y-axis and time on x-axis can be plotted. Once the concentration of both the reactants and products stops showing the change, so there is no change. How much the concentration of product is there, that much only it has remained. How much the concentration of reactant is there, that much only it has remained. So once this concentration, change in the concentration stops, chemical equilibrium is achieved. And chemical equilibrium is what? It is dynamic in nature. So based on the extent to which the reaction proceeds to reach the state of equilibrium, these may be classified in 3 groups. Yes, it may be classified in 3 groups. The reactions which proceed almost to completion and concentrations of the reactants are left are negligible. Then the reactions in which most of the reactants remains unchanged, that is only small amounts of products are formed. The reactions in which concentrations of both the reactants and products are comparable when the system is in equilibrium. See, I cannot always say that when equilibrium is attained, reaction or concentration of a reactant will be equal to concentration of the product. No. In some cases at equilibrium, what may happen is the concentration of a reactant may be more than concentration of product. That means, suppose the reaction is progressing in forward direction and here it is progressing in less amount in, so rate of forward reaction is less than rate of backward reaction. So this might be achieved. Sometimes the concentration of product is more than concentration of reactants. When reaction is progressing in forward direction. Here reaction is progressing in more in backward direction, therefore concentration of the reactant is more. Here it is progressing in forward direction, therefore concentration of the product is more. Sometimes both the concentrations of reactants and concentration of products are comparable, neither very more nor very less. So they are what? They are comparable. So this all terms we will come across in detail when we are studying all the concepts of chemical equilibrium. So I hope whatever I have explained till now, everything is being cleared. Yes. So first thing what we discussed is there should be reversible reactions. So reversible and irreversible reactions means what we have seen. Then in reversible reactions, we have 2 reactions. One is forward reaction and another one is backward reaction. In irreversible reaction, it progresses only in one direction. That is what? Forward direction. Yes. And then we have seen the equilibrium and its dynamic nature. And we have understood what is equilibrium. Either if you want to speak in terms of concentration, you can say concentration of products and concentration of reactants remains constant. And this is the graph to make it understand concentration of reactants and concentration of product. So with the time, concentration of reactants goes on decreasing. With the time, concentration of product goes on increasing. A state is reached where both the concentrations of the reactants and products remains same. That is state of equilibrium. If you want characteristics, these terms will define how to explain the equilibrium. When you vary these, there will be change in the equilibrium state. And equilibrium has to be carried out, must and should. Equilibrium must and should be, the reaction must and should be carried out in a closed vessel. Yes, because matter does not get escaped. Only for reversible reactions we can explain the state of equilibrium. Equilibrium state is achieved, and equilibrium attained is what? It is dynamic in nature. That means at equilibrium state, the rate of forward reaction is equal to the rate of backward reaction. And this is the graph to explain the rate of reaction with time. So with the time, forward reaction goes on decreasing. With the time, backward reaction goes on increasing. At certain time, the rates of both forward and backward reactions remains constant, and that is called equilibrium state. Yes, and we have seen types of equilibrium: thermal equilibrium, mechanical equilibrium, physical equilibrium, and chemical equilibrium. In this topic, we are going to discuss only on these two. Moreover, we'll be concentrating on chemical equilibrium. We'll just brief out physical equilibrium and we'll be concentrating on chemical equilibrium. The further parts of the concepts I'll be taking up in the next video. Hope you have understood till here. Please practice the concepts. Thank you.